My name is Vikram, and today I'm going to be talking about Living IoT, which is a wireless sensor platform that is small enough to ride on the back of a live insect like a bumblebee, like you see here. So in this work, we asked ourselves the question, what if IoT devices could fly? Now, the reason we'd like to make sensors fly is we can look at all of the emerging applications for drones, like smart farming, pipeline inspection, and disaster recovery. But the issue with drones is that they have a pretty limited battery life right now, and most commercial drones can only fly for 10 to 20 minutes. The reason for this is because flight is very power expensive. For something like the DJI Phantom drone, it takes about 100 watts or so to fly. So that means that you need a pretty large battery. But you also can't make that too big because then it takes more power to lift that battery. This problem also becomes even more pronounced when you shrink down the drone because propellers start becoming more inefficient at this scale. These smaller drones only last about 5 minutes. And then you have other alternatives that use flapping wings in some research prototypes, and these are not quite at the point where they can carry their own battery. So really, the takeaway here is that it is fundamentally hard to make something fly for a long time. If we look to nature, though, all around us, we can see small insects like this blowfly that are capable of flying for hours just based on the tiny amount of food that they eat. And these are some of the most agile flyers in the animal kingdom. And on top of that, there are other insects like bees that regularly fly around carrying a pretty heavy payload for their size. So our idea here is to leverage live insects to actually carry sensors in places like farms. When the bees fly around searching for food as they normally would, we collect sensor data and store it locally on our electronics that are attached to the bee. And then when they come back to the hive, we can upload that data wirelessly to an access point and then recharge the battery wirelessly. So in this work, we're getting around the issues of drone battery life by taking this bio-based solution where we don't have any need for mechanical propulsion and we can instead focus our energy on sensing. Also, we can leverage the fact that bees are already introduced on farms and they understand a lot about their environments and things like plant health as well. So here's a video of a live bumblebee carrying one of our sensors. Right now it's flying around in a little container. So when building this platform, we had two major challenges we had to address. And the first of these was making this whole thing relatively lightweight and low power, because the bees that we used can only carry about 100 milligrams of weight. Then within this weight budget, the only battery that fits weighs already 70 milligrams, and so that leaves about 30 milligrams for all of our electronics. The second challenge is that unlike drones, bees do not come with a remote control. And while researchers have shown that larger insects like moths and some large beetles can be controlled, this has never been done for anything as small as a bee. So instead, we take a different approach and we do opportunistic sensing, where because we get flight for free, if we can compute the location on the bee as our sensor flies around a farm, when it gets close to a point of interest, we can record a data point. So I'm going to go into more detail about our solutions. The first is how we build the lightweight hardware, and second is how we track the location of the bees in 2D. So let's look at how we actually build this thing. Now, before I get into too much detail, I want to back up and look at hardware in this space a little bit more broadly. There's been a trend in the past few years, starting with ambient backscatter and other follow-up works like FreeRider, in trying to push the power required for communication lower and lower using backscatter. But the problem is that these things still weigh tens of grams. And for mobile sensors, we have this new problem formulation where we like to make things as small and light as possible. So one solution would be to develop a custom IC, but that requires a pretty expensive and long design cycle, taking at least a year or more. And then also, this still would need external components and things like a battery. So what we really want is something more programmable and general purpose. Think something more with the flexibility of a software radio, but where size and weight become the primary design constraints. So to build this, we use a general purpose microcontroller that can do both computing and the control that we need. We use this to read data from our sensors, and we use it to support backscatter at ranges of up to a few meters, all within a package of about 30 milligrams or less. To go into a little bit more detail, we use our microcontroller's onboard ADC to read the output of our passive amplitude-based receiver. That gives us a downlink. And we also use it to control our backscatter switches and toggle between two impedance states to transmit data. And last, of course, we have a switch to select between TX and RX modes. On top of just choosing very small components, we also have to build a very lightweight PCB. And the way that we do this is we do this in-house using a laser micromachining, using this 355 nanometer UV laser that can cut traces down to about 10 microns, or features 10 microns or smaller. And we start by etching out the copper traces on a piece of thin piece of copper-coated FR4, and then we place the components and use a hot plate to solder everything. So now that we've seen how we can build these tiny circuits, let's look at how we can actually track where the bees are going in 2D. When designing the localization system, we started off with the decision that we wanted to build something that could localize itself. Because if we can do that, then we can easily scale up to larger numbers of devices. Think we want something like the architecture of GPS. The problem with GPS itself, though, and really any other radio, is these things tend to be large and power expensive. So what can we do at very low size and power? Our solution is to use this passive receiver circuit that can give us the envelope of an RF signal. Now, this is great from a power and size perspective, but it introduces this new problem that we only get amplitude information. And from what we've seen in prior work, purely RSSI-based localization methods tend to give pretty poor accuracy. So the question is, how can we get some kind of phase information and compute 2D location using only this amplitude that we get? The way that we get some angle information from our envelope detector is we take inspiration from backscatter and push complexity to our access point. By using an AP with multiple antennas, we can sweep across different phases. Or to put it differently, we can essentially beamform our output across different angles. And when that angle aligns with the B, we get a maximum on our receiver. And then by combining two APs with known positions, we can actually get the location of the B. Now for addressing multipath, we note 2 points here. First, in the case of farms, in the scenarios that we tested, the line of sight path is strongest. And we also we proved that even with some multipath in these cases, the error remains bounded if you add a few antennas. The second thing is that for expanding to other applications, we could try applying this technique over different frequencies to account for multipath as well, and relax that constraint of assuming that the line of sight path is strongest. To evaluate how well this works, here's a plot showing our angular accuracy on the y-axis versus range on the x-axis. We tested this in an open soccer field here at a distance of up to 80 meters at a few different flight speeds, and these are in the range of what a live bee would actually be flying at. And we see that in most of these cases we get less than 10 degrees error for angular accuracy. To give a few additional specs of our system, it can store up to 8,000 humidity and location data pairs. It can run for about 7 hours when sampling at a rate of once every 4 seconds. And our harvester could recharge a battery in about 6 hours when it comes back to the hive. So to summarize, our contributions are we show for the first time that insects can be used to carry general purpose sensors. We also design a novel, low-power localization technique. And finally, we build a lightweight programmable platform for doing all of this computing, communication, and sensing. So what's next for this sort of work? We hope that this opens up a new space with a variety of different research questions. For example, what other sensors can we use? Could we, for example, put a camera on one of these insects? Could we stream that data in real time? And could we use this sort of technology to build a biohybrid robot? And last, but perhaps most importantly, we can see that as climates and habitats around the world are beginning to change, many biologists need tools to be able to study how this is impacting animals, and particularly insects. But at the moment, there really aren't any very lightweight computational tools that they can use to study these problems. And we're in the process of working with biologists to show how we can use this platform to learn more about insects as well. So thanks, and with that I'd like to conclude with also adding a brief note that the bees that you see in these videos were actually wild bees that we caught, and after finishing our work we were able to take off the sensors and release them back into the wild.